Welcome back. So, in the previous lecture, we had seen the need for the imaginary number, and we saw that it was very essential to solve. So, in our example, the cubic equation, but imaginary number is required to solve sometimes to find the real roots of real polynomials via the formula. So, let's proceed from where we left. And that also motivated us to expand the polynomials to complex polynomials and look for roots of complex polynomial, and we had made a remark that the complex numbers is algebraically closed in the sense that we don't have to look any further. All the roots of complex polynomials will lie in the complex plane. So this is the statement of fundamental theorem of algebra, and the purpose of this lecture is to give you a proof of the fundamental theorem of algebra. So let's start from where we left last time. So we stopped with the cubic equations. So let's start with the fourth degree polynomial, which is the quartic equations. So the formula for roots of the fourth degree equation was solved by Ferrari much earlier, and in fact this was even published before the result of cubic equation was published. But as I said, the cubic equation was published, the formula was published much later by Cardan, uh, right, by Cardano, after he had obtained it orally, and actually after several years. So the formula for quartic equation was published before cubic equation, and in fact the proof is also probably is kind of simpler than the cubic equation. So the roots of the quartic equation is given by, so the x is the unknown, so the x can be obtained by solving these two quadratic equations. Okay, so you have a quadratic equation satisfied by x, so any root of this quartic equation are actually the roots of these two quadratic equations. So you have two roots from here, you have two roots from here, so you have four roots for the original equation. And in this quadratic equation, you have what is called a capital A and a capital C and this y. So otherwise what you have, this A is just the coefficient of, the little a is just the coefficient of x cube here from the equation. So what are this capital A, C and y? So capital A is a square over 4 minus b plus y, where this minus b is again the coefficient of x square. C is y square over 4 minus d, where d is again from the coefficient. So what is now unknown is the y. Y is a solution to this cubic equation. So to solve for x, you plug in for a, c and y from these, and AC is obtained from the coefficients and this y, and this depends only on the coefficients of the quartic equation. And in this cubic equation you will get three values for y. Whatever value you choose, you get the same value for x, so it doesn't matter which root you choose for this cubic equation. So you solve this cubic equation, choose one of them, choose any one of these roots of this cubic equation, use that as an y, and then you can solve for these quadratic equations. You have the roots of the quartic equations. Okay, so this is just whatever I said, that you will have three choices for y, every choice will give you the same root. So that settles quartic equations, no issue. And then what happens to the quintic equations, the fifth degree and so on. So sorry, here I'm just saying again that whatever roots you take, you will get, and you solve for x, you get the roots of this quartic equation. So polynomials of degree 5 and more, quintic and more, right? So after the fourth degree was solved, as you can see, it's in the mid 16th century, we had known the formula for cubic and quartic equations, and then people started looking for degree 5 equation, I mean formula for degree 5 and more and further. And finally in 1823, so almost after 300 years, um, Abel showed that no such formula exists for the roots of a polynomial of degree 5. So when he says formula, what he means is that you cannot have an expression which involves only elementary operations and extraction of roots, right? So that is what you have been seeing so far as formulas, right? Whether you look at the quadratic equation formula or the cubic equation formula, all that you did was additions, subtraction, multiplication, division, taking square root, cube root, and all that, right? So you're only doing these kind of elementary operations, and this is what precisely you mean when you say formula. And Abel showed that you cannot write an expression or a formula like that for the roots of fifth degree polynomial. This he showed in 1823. Abel showed it. Within a span of 9 years, at the age of 1819 actually, Galois showed that in fact no such formula can be written not just for polynomial of degree 5 but for any polynomial of degree 5 and greater than 5. You cannot write a formula for these polynomials for the roots of these polynomials. This he showed in 1832. So that is the beginning of what we today study in Galois theory course. So the theory of Galois is precisely looking at polynomials, the symmetry, symmetry in their coefficients and so on. Okay, so it's a different way of doing stuffs, which is taken up by the algebraic course, right? I mean, if you do a course in algebra, Galois theory, you will see the other parts of this. So it looks like, so we were looking for formula after fourth degree, and finally it turned out that you cannot write down a formula. So now that reduces the question to existential nature, in the sense that okay, I cannot write down the formula. How many roots do we have for any polynomial, for any degree polynomial? How many roots do we have? Even if we cannot explicitly write down the formulas, can we say something about the existence of roots? Do all polynomials have roots? Like we have already seen in the quadratic case that when the discriminant is negative, you don't have any real roots, so there is no real roots. And the way we gave a sense of roots there was to extend the notion of roots to the complex domain, and then we show the existence of two complex roots. So now we are asking the question here in that sense, right? Okay. So this was the development historically also. Earlier people are only looking for real roots, and then slowly looking at various these equations, they realized that okay, this question has to be expanded into the complex zone, complex domain. So now the question is, how many roots do we have, including real and complex roots? How many roots do we have? So far it looks like we will have exactly as many roots as the degree of the equation. Is that true? Can we prove it? Right, and that is the statement of fundamental theorem of algebra, which actually says that the complex numbers is algebraically closed. So though it's a fundamental theorem of algebra, it's a result of analysis. The proof is actually a result of analysis, and this is an analysis course. So let's start with this proof of this result. Okay, so I'm going to assume things because, as I said, we are in a course where you have already come across many of these analysis contents of this course, like real, complex, and other things. So we will use it. So we will not follow any logical structure order, but we will kind of hop back and forth. Okay. So what is a complex polynomial now? So a complex polynomial of degree n is just ai zi where it's summed over from 0 to n. So you have a z an z power n plus an minus 1 zn minus 1 and so on up to a0, right? So you have this sum of n plus 1 terms here. So this is where these AIs are all given, and now they are all complex numbers. So we have just expanded into the complex domain now, right? I mean, the previous lecture, if you have seen the definition of polynomial, we had given it in the real variable set, right? So same definition works for the complex variable set. So this is a polynomial of degree n. Okay. Now, there's an interesting property of this polynomial is that these polynomials are unbounded in C. In C or in R, I mean, it's true even in R. So they are actually unbounded in the sense what I mean by unbounded is that as you approach infinity, the polynomials also blow up, right? They also approach infinity. And a quick way to see this is just right. So if you see this is your polynomial, then pz can be written here like this. What we have done here is just taken the leading, I mean, nth degree variable outside. So once you do that, you have an here because zn goes out. So I have taken a mod here. So um, just to show that, I mean, mod itself is going to infinity. So I've taken mod z power n. So what you have here is the powers of z in the denominator after the first component, after the first term. So now when we take the limit mod z goes to infinity, you see that whatever is here in here, all the terms from the second goes to 0, right? Because this goes to infinity, it's all in some 1 over z form. So, and as z goes to infinity, all the denominators here goes to infinity. So all these terms goes to 0. What remains is just an. And now what happens to mod zn? The same thing. As z goes to infinity, mod zn goes to infinity, right? Which means that as z goes to infinity, the polynomial goes to infinity. Which means any polynomial is unbounded in C. So they blow up. This is another way of looking at the fact that the polynomials are bounded. Like you know that whenever zn goes to infinity, whenever z goes to infinity, z power n goes to infinity. So this whatever you have here, so the denominator here goes to infinity, and the fact that polynomials unbounded means that this ratio is actually 1, right? Which means both go to infinity. They cancel out each other. They go at the same rate. Okay, so this is the fact about polynomials being unbounded. With this, let's get into the statement of fundamental theorem of algebra. So what does fundamental theorem of algebra say? It says that any non-constant polynomial, so non-constant, as I already explained in the previous lecture, that any constant function, if it's a zero constant function, it has infinitely many zeros. It's a trivial case, you remove that. And any other constant polynomial will not have any zero. So every non-constant polynomial with complex coefficients of positive degree admits at least one complex root. So this statement is actually enough. So what we are saying here, we are not talking about exactly n roots. I mean exactly as many roots as the degree of the polynomial. We are just saying that any non-constant polynomial of whatever degree will admit, degree bigger than or equal to 1 will admit at least one complex root, right? And this statement is enough to conclude the fact that you have exactly as many roots as the degree. Why? Because if you take, right, this is what I'm saying here, that the first statement is enough to conclude that any non-constant polynomial has exactly as many roots as its degree, counting multiplicities. This is again I talked about in the previous lecture, that multiplicity is the double root, triple root, the multiple roots, right? I mean, it's a root of the polynomial and also its derivatives and so on. So how do you see this fact that proving the existence of only one complex root is enough? Because suppose, say, we have the polynomial pz and z0 is a root of this polynomial, then automatically pz has this form, right? Because when z is equal to z0, z is equal to z0, pz0 is 0, and here again this is 0. So this p can be factorized like this, and where this q is a polynomial of degree less than p, 1 degree less than, so it's a degree of n minus, so it's degree n minus 1. Now you apply this fundamental theorem of algebra again for this n minus 1 polynomial q, which will again admit a root. Now that q will also have the form like this for a new roots, let's say z1. So then you can rewrite q as z minus z1 into some rz polynomial which is of degree n minus 2, and apply this first statement result for r and so on. So just showing existence of one complex root is enough to actually show the existence of exactly as many roots as the degree of the polynomial. Okay. So the proof of the fundamental theorem of algebra was first given by Gauss. I mean, first correct proof was given by Gauss for both real coefficient and complex coefficient and so on. Now today we are going to look at a very simple, very short proof. That's a very, I think the shortest proof that I know of fundamental theorem of algebra, which is nice. So let's look at the statement. So you have a polynomial p from C to C which is non-constant with constant coefficients, of course. Then there is a complex number z0 such that p of z0 is 0, right? And this is what we need to prove. We just need to show at least one root exists, right? So let's so the statement is there is a z0 such that pz0 is 0. So we are going to prove this by contradiction. So what we are going to do is that let's assume that p is not 0 for any complex number. So suppose pz is not equal to 0 for all the complex numbers. Okay, so there is no z0 such that this happens. So let's start with that assumption. So if pz is not 0 for all z, then I can talk of its reciprocal. So I can define this new function q, which is 1 over pz, right? Which is 1 over pz, and you see pz is a polynomial and you know it's actually a holomorphic function, and if it's not 0 at any point of the complex number, then q is also a holomorphic function, like there is no singularity or pole or anything here because p is non-zero. So q is also an analytic, I mean a holomorphic function. Yeah, same as I'll be saying analytic. It's an analytic function on the entire C or holomorphic function on the entire C. So this entire function basically means it's holomorphic in the entire C. So it's an holomorphic function or entire function. So this q is an entire function, which means that it satisfies the Cauchy integral formula, right? So what does Cauchy integral formula say? Cauchy's integral formula says that if you have a holomorphic function, then then for any point, and if you have a closed curve, then for any point in the interior of the region bounded by the curve can be computed just by knowing the values on the curve itself. So knowing the values on the curve is enough to compute every value uh, every value of the function at every point inside the curve. So inside the region enclosed by the curve. Okay. So this is something I'm assuming you know. We will do this later. So as I said, I'm not going to follow the order. We will do this Cauchy integral formula in the later lectures. So this is just for completeness. We will just uh, give it here. We will assume that you know this formula. Okay. Of course, you know it because you must have already seen it in the complex analysis course that you might have done before. So what does this mean? This means that so by Cauchy's integral formula for all r positive, uh, the value of q at 0, so I'm going to take the unit circle. So the closed contour that we take is the circle, no, sorry, not unit circle, the circle of radius r, right? So I can fix any r, so I can do this for any r. So for any r, you take the circle of radius r, which means origin is in the interior of that circle. So by Cauchy's integral formula, the value of q at 0, which is an interior point, is 1 over 2 pi I integral over that closed contour circle qz by z, right? So here it's z minus 0, right? So that 0 is what is taken here, so it's actually qz by z. And this is valid because q is an analytic function. Now it's an holomorphic function for us. So now let's compute this. So use this fact that your z is a complex number. So in the polar form, it has r e power I theta, and if the z is and the z is actually sitting on the circle of radius r, so the magnitude is always r. Only the theta only the theta is changing. So if you use that polar form, you actually have a one variable integral, right? So this becomes 1 over 2 pi q r eta. So here what we have used is there is a z here which is r e I theta, and there is a dz here which is I e I theta, r I e I theta. The r and r here is cancelled. The I here and this I here cancels out, and the e power I theta also cancels out. So what remains is just this, and this limits of the integral is now in the theta variable. Okay, so now this is this. Now this is again an analytic function, and now what you do is you take the limit. So this formula was valid for every r, right? So you let r go to infinity. So you do it for circles getting bigger and bigger. So when you let r go to infinity here, the integral on the RHS tends to 0, right? Yeah, right. So when you let r go to infinity, what you have is the RHS integral tends to 0, right? And why does that happen? Because by the definition of q here, q is 1 over pz, right? P is unbounded. So when r goes to infinity, that basically means that mod z goes to infinity. So when mod z goes to infinity, pz goes to infinity, which means qz goes to 0. So as r goes to infinity, this quantity here goes to 0, right? Whereas this is on the LHS here. So this goes to 0. So this entire quantity becomes 0. Whereas what you have here is q0, which is non-zero because q0 by definition is 1 over p0, right? So this is because if this has to be 0, p0 has to actually attain, this has to be infinity, which is not the case, right? So p0 is actually is the constant, that whatever you have, that a0 that you had. So this is a non-zero number. if you assume that. So this is a contradiction. So we started with a wrong assumption here. We started with an assumption here that is non-zero. That is false because we have a contradiction here. So this shows that any complex polynomial will have at least one complex root, and that uh, proves the fundamental theorem of algebra. So we will stop here. Thanks a lot.